What if everything you've ever been told about the beginning of the universe is only part of the story? Stay with me, because this isn't just another space theory. This is a shift in how the smartest physicists on Earth now understand reality itself. For decades, scientists insisted that asking what came before the Big Bang was meaningless. According to them, the Big Bang didn't just create matter, it created space and time too. So asking what came before was like asking what lies north of the North Pole. There simply was no before because time itself didn't exist yet. But that idea is no longer as solid as it once seemed. Today, a growing number of leading physicists are stepping away from that explanation. In fact, recent discussions among top experts suggest that something may have existed before the Big Bang, and uncovering that possibility is becoming one of the most fascinating developments in modern science. To understand why this shift matters, we need to clear up a major misunderstanding. When most people talk about the Big Bang, they imagine a single moment, the absolute beginning of everything. But in physics, that moment is actually made up of two very different concepts that are often mixed together. First, there's what scientists call the hot Big Bang. This refers to the early stage of our universe, when everything was incredibly dense and unimaginably hot. And this part is not speculation, we have strong evidence for it. We can still observe the faint afterglow of that phase today, known as the cosmic microwave background radiation. It's one of the most studied and reliable signals in all of physics. But then, there's the second concept, the singularity. This is where things become far less certain. The singularity is a mathematical point where the laws of physics, as we know them, completely break down. Density becomes infinite, temperature becomes infinite, and the equations stop making sense. For a long time, this singularity was treated as the true beginning of time itself. But now, scientists are starting to question that assumption, and that's where this story takes a truly unexpected turn. Because once you separate the hot Big Bang from the singularity, everything starts to look very different. The hot Big Bang is strongly supported by evidence. It marks a real phase in the early universe that we can still observe today. But the singularity is another story entirely. It may not represent a true beginning at all. Instead, it could simply be a warning sign that our current mathematical models are incomplete. In other words, when the equations break, it doesn't necessarily mean reality begins there. It may mean our understanding ends there. And if that's the case, then something could have existed before what we've always called the beginning. That single possibility has pushed physicists to explore new ideas. And one of the most fascinating comes from Roger Penrose. His theory, known as conformal cyclic cosmology, suggests something bold. Our universe is not the first, and it won't be the last. According to this model, what we call the Big Bang was not the true beginning of everything. It was a transition point, a bridge between one cosmic era and the next. Penrose describes each of these eras as an aeon. Each aeon begins with a Big Bang, expands over unimaginable lengths of time, and slowly evolves toward a very unusual ending. Over trillions upon trillions of years, all matter in the universe gets pulled into supermassive black holes. These black holes don't last forever, though. Through a process known as Hawking radiation, named after Stephen Hawking, they gradually evaporate. Eventually, after an incomprehensibly long time, the universe is left almost empty. No stars, no planets, no matter, only radiation remains. And this is where Penrose's idea becomes truly extraordinary. Because at that stage, the universe begins to behave in a way that completely challenges our intuition. Because once a universe reaches that state where no matter remains and only radiation exists, something deeply counterintuitive begins to happen. Without mass, there's nothing left to define scale. Size, distance, even the flow of time as we understand it, all lose their usual meaning. In that strange, empty condition, an infinitely large universe becomes mathematically indistinguishable from an infinitely small point. And that idea sits at the heart of Roger Penrose's theory. What he proposes is both simple and profound. The end of one cosmic era can become the beginning of the next, not symbolically, but through exact mathematical relationships. As the universe thins out into pure radiation, it can be rescaled in such a way that it effectively resets into a new Big Bang. This process is known as conformal rescaling of space-time. So instead of a universe starting from nothing, it emerges from the final state of a previous one. The death of one universe becomes the birth of another. Now here's where things move from theory into something even more intriguing. In 2025, Penrose, along with physicist Christoph Missner, explored whether traces of a previous universe could still be visible today. Their work suggests that certain patterns in the cosmic microwave background, the oldest light in our universe, might carry information from before our Big Bang ever occurred. Specifically, they examined unusual hotspots in this background radiation. These are tiny regions that appear slightly warmer than their surroundings. According to their calculations, These spots could be linked to massive black holes that existed in a previous aeon. As those black holes evaporated, they may have left behind faint imprints that carried over into our universe. If this idea holds true, it means we're not just imagining what came before, we might actually be observing its fingerprints in the sky. That possibility alone changes how we think about the universe, but it's not without controversy, and not everyone is convinced. Not everyone is convinced by Penrose's model, and that's important to understand. Some researchers argue that those temperature variations in the cosmic microwave background can be explained using standard physics without needing a previous universe at all. The debate is still very active, and no single explanation has been confirmed. But what makes this moment in science so fascinating is that these ideas are no longer purely philosophical. They're being tested against real data. And while Penrose's theory is elegant because it works within Einstein's framework, another major idea takes a completely different path to answer the same question. This brings us to the Big Bounce, a theory built on a framework called loop quantum gravity. While Einstein's theory of general relativity has been incredibly successful in explaining gravity and the large-scale structure of the universe, it struggles under extreme conditions, especially when everything is compressed into an incredibly small space, like at the supposed beginning of the universe. That's where the equations stop working and produce the singularity. Loop quantum gravity tries to solve this by bringing quantum mechanics into the picture. And when you apply quantum principles to space-time itself, something surprising emerges. Space is not smooth or continuous. Instead, it's made up of tiny, discrete units, almost like a fabric woven from the smallest possible building blocks. This means there is a limit to how much anything can be compressed. There's a smallest possible volume, and nothing can go beyond it. That single idea changes the entire story. In Einstein's equations, if you go backward in time, the universe keeps getting denser without limit. But in loop quantum gravity, there's a stopping point. Once the universe reaches a maximum density known as the Planck density, something unexpected happens. Gravity, which had been pulling everything inward, flips and becomes strongly repulsive. And when that happens, the universe doesn't collapse into nothing. It rebounds. It rebounds outward in a powerful expansion, what physicists call the Big Bounce. Instead of a singular beginning from nothing, this model suggests our universe emerged from the collapse of a previous one. As that earlier universe contracted and reached the maximum possible density, quantum effects took over, reversing gravity and triggering a new expansion. What we observe as the Big Bang could actually be the aftermath of that bounce. This idea was first demonstrated mathematically in 2006 by researchers including Abhay Ashtekar, Tomasz Pawlowski, and Parampreet Singh, and since then, it has been refined by teams around the world. But what makes this theory especially compelling today is how scientists are beginning to test it using modern technology. Instead of relying only on equations, researchers are now using powerful supercomputers to simulate extreme cosmic conditions. In 2025, teams from King's College London, Queen Mary University of London, and University of Oxford published major work using a method called numerical relativity. This approach allows them to solve Einstein's equations in complex scenarios that would be impossible to handle by hand. One of the leading scientists involved, Eugene Lim, described traditional methods as being like searching under a streetlight. You only look where it's easiest, not where the answers might actually be. With numerical simulations, researchers can now explore those dark regions, modeling conditions that go far beyond simplified assumptions. And the results are pushing boundaries. These simulations don't just explore bouncing universes, they also test whether our universe might have interacted with others. Scientists are searching for subtle marks in the cosmic microwave background, sometimes described as bruises in the sky, that could reveal past collisions between entire universes. And this is where the story takes another turn, because while scientists look into the past, new discoveries are also reshaping our understanding of the future. And that future might be far more connected to the past than we ever imagined. Because while scientists are exploring what could have existed before the Big Bang, they're also uncovering new evidence about where our universe is heading. In 2025, the Dark Energy Spectroscopic Instrument released one of the most detailed maps of the universe ever created, tracking nearly 15 million galaxies and quasars across billions of years of cosmic history. This massive dataset is helping researchers understand one of the biggest mysteries in physics: dark energy. Dark energy is the force responsible for pushing the universe to expand, and for a long time, scientists believed it was constant and changing over time, built directly into Einstein's equations as the cosmological constant. But new data is beginning to challenge that assumption. When researchers combined these observations with other measurements, they found growing evidence that dark energy may not be fixed. It could actually be weakening. Now, if that's true, the implications are enormous. A weakening dark energy means the expansion of the universe could eventually slow down, and if it slows enough, it might stop together. From there, gravity could take over, pulling everything back inward. The universe would begin to contract, growing hotter and denser, eventually collapsing into what's often called the Big Crunch. And if the Big Bounce model is correct, that collapse wouldn't be the end, it would trigger the next expansion, the next universe. Physicist Henry Tai and his team have even modeled this possibility, suggesting such a collapse could occur in about 19 billion years. On a human scale, that's unimaginably far away. But in cosmic terms, it suggests our universe may already be somewhere near the middle of its lifespan. Now, to be clear, none of these ideas are confirmed. The evidence is still developing, and scientists continue to debate every detail. But one thing is certain, this question is no longer beyond reach. For the first time, we are not just wondering what came before the Big Bang, we are actively searching for answers, using data, mathematics, and the universe itself as our guide.